Hi everyone, my name is Pradyumn and today we will discuss the Leetcode contest which was bi-weekly of this week, and we'll discuss all the problems A, B, C and D. Okay, and before we start, I will tell you about our courses at TLE Eliminators. So if you are someone who is stuck at just solving one or two problems per contest in competitive programming and you want to level up, then our self-paced courses are exactly what you need. We have structured this program into 4 levels, so you can start from wherever you are: beginner, pre intermediate, intermediate, or advanced. You will learn the most relevant CP concepts through recorded video lectures, followed by carefully curated practice problems, combined with guided hints and detailed video solutions that help you understand the why and not just the how. We believe in we believe in helping you build real intuition. If you need more help, then you will get instant doubt supports from our higher ed mentors, so you are never left stuck without doubts. And beyond learning, you can enjoy leaderboards, progress tracking, internal contests, and PCDs to keep you consistent. So pick the level that fits your needs and start learning today. And if you're not sure that which level is fine for you, then you can watch this video on how to choose this level which suits your needs. And more than that, you can also explore the syllabus of each level and the prerequisites, difficulty and all, and also you can watch the video about that. Okay, so anyways, let's start the PCD now. So let's discuss the first problem. Just 1 second. Yeah, so this is not the first problem. Okay, so this is the first problem of today. You are given an n cross m grid and an integer k. A sensor placed on cell R, C covers all the cells whose Chebyshev distance from R, C is at most k. This distance is defined as max of R1 minus R2, C1 minus C2, absolute value. Okay. Your task is to return the minimum number of sensors required to cover each cell in the grid. So what they are saying is that you have a grid. Okay. You have a grid of size n cross m. Right. You have this grid of size n cross m. I'm audible, right? Just let me know. Hi guys, am I audible? Hello, hello, hello. Just let me know, guys. Okay, I am audible. So yeah, let's see. So we have a grid of size n by m, right? That means it has n rows and m columns. Okay. So a grid like this, we have a grid like this. Just don't judge my drawing. So it has n rows and m columns. And what they're saying is that if you place a sensor in some cell, okay, in this cell, let's say you place a sensor at the cell x1 comma y1. Okay, then this sensor will cover all the cells I comma j such that the max of basically the distance between these two distance is defined as what? I minus x1 comma j minus y1 comma odd. So the maximum of those, basically that's the distance that they are defined. So if that is less than equal to k, then the x1 y1 sensor covers the point I comma j. Okay, so we have to determine that what is the number of sensors, minimum number of sensors, such that that we need to place on this grid such that it covers all of the points in the grid. Okay, so this inequality, like this distance, is quite interesting. Like if you make physical sense about it, then this problem becomes very easy. Okay, so let me ask you guys some things. I'll draw a grid. So I'll just take one cell and I will uh, just see that what cells are there which are at Chebyshev distance of 1. Let's say this cell I am choosing. Okay. Let's say I place a sensor at this cell. So, guys, can you tell me that which cells are there which are at a distance of 1 from this? Distance mean by this definition. So, which cells are there at a distance of 1 from this cell? Can you answer me? Basically, I can say that all of these cells, okay, like if you see, all of these cells are at a distance of 1 from this cell. If we take the max of x difference and y difference, okay, like here, this is here both are 1, x and y difference both are 1, so max is 1. Then here x and y, like x is 0 but y is 1, so the max is 1. So basically all of these cells are at a distance of 1. Okay, so I'll mark 1 here, I'll draw 1. Okay, then what cells are at a distance of 2? So basically all of those cells, like all of these cells essentially, all of these cells are at a distance of 2. Like I'll just draw this thing. So all these cells are at a distance of 2. Okay, so like if we want that all those points which are at a distance of less than equal to k from this sensor, then what is that? Like let's say k is equal to 3. Okay, then on this grid, what are the cells which are, like what is that group of cells which are at a distance of less than equal to 3 in this grid? Like I'll make a bigger grid. Okay, is there any shape like this? Okay, yeah, there is there. What is this? Okay, never mind. I'll just draw the grid by hand. So let's say this is the grid. Okay, then if you choose any point, like let's say you chose this point, you chose this point as your origin, and you want to find out that for k equal to 2, like which points are there which are in the distance of k equals to 2. So like my claim is that okay, these ones are at a distance of 1, these neighboring ones, right? So they are definitely there, and the neighboring ones to that, they are at a distance of 2, so they are also included in that. So basically the square which is like this square right here, if you see this square right here, this is the one which our sensor controls. Okay, and it is centered at this point where our sensor is. So like when we keep a sensor at this point, then all of those points which are in this square centered at this point and also having the side length 2k plus 1, like here k distance, this one cell, and here k distance basically. So that's why side length is 2k plus 1. So if we place a sensor at this point, having, like if we place it at this point, then the square with side 2k plus 1 and center this will be covered by this sensor. So is it clear until here? Like 5 minutes I guess. Guys, just let me know. um, Others, like just tell me if you don't get it, that how we got this square Okay. So yeah, that's the entire point. So my point was that in the grid, whenever you place something, whenever you place a sensor at some point, then it will control the square centered at that point, having side length 2k plus 1. So let's say this is your grid and your k is given to be 1. Okay. So basically you can put a square of side length 3. Like essentially the problem boils down to, you can place squares of side length 3 on this grid and you have to cover all the cells, right? And you have to find the number of squares, correct? So let's say this is the grid. Then what you will do, you will place one square right here, then one square like this, then let's say one square like this of 3 by 3, right? And one square like this, and then one more to cover, like these cells are uncovered, right? So I have to cover them also. So like this. So basically I used 6 squares to cover this grid, right? So but in general, what is the answer? So let's think about 1D case. Let's say the grid was not a grid, but it was an array. Like basically one, it's a strip. Okay. It's a strip of length n. And I can place 2k plus 1 length rectangles. Right. So in that case, how many rectangles will I need? Like in this case, just let me know the answer. If I have a strip of length n and I can place rectangles of size 2k plus 1, length 2k plus 1, then how many rectangles do I need to put on this strip? Let me know. What is the answer? Their division. Yeah, basically n upon 2k plus 1. Like basically you will place one rectangle right here of side 2k plus 1, then one right here, then one right here. So basically n divided by 2k plus 1. But if there's a remainder, you will need one more, right? Like let's say you had 7, 1, 2, 3, 4, 5, 6, and k equals to 1. So 2 plus 1 is 3. So you have like length 3 rectangles you can put. So you will put one here, then you will put one here, and then this one is remaining, right? So you need one more. So basically if there is something remaining, then the answer will be plus one of that. Like basically you can say ceiling function of this, right? Ceiling function of n upon 2k plus 1. Like if there is no remainder, then the answer is n upon 2k plus 1. And if there is some remainder like this, then the answer will get plus 1. So ceiling function is that thing only, right? Okay. So this is for 1D case, right? But what about 2D? Like in 2D case, how many squares would you need? So I think it is quite intuitive that, see, because you need to like cover all these squares. Like let's say, so let's say here you have how many rows? 1, 2, 3, 4, 5. 5 rows, and 1, 2, 3, 4, 5, 6, 7. 7 columns. So and let's say k equals to 1. So your 2k plus 1 is 3. Like square of side length 3. So now of course you need to cover all 5 rows, right? All 5 rows you need to cover. So along this direction, you will need 5 by 3 ceiling, which is 2. Like you will need 2 squares along this direction in every column, basically. Like not in every column, but something like this. Like one square here and one square here. So using these 2 squares, you can cover all the rows in these 3 columns, right? So 2 is that thing. And along this direction, you will need 7 upon 3 ka ceiling, which is basically 3. So like you need three squares along this direction, which may like basically you can see something like this, that if you want to fill all the columns, then you will need one square like this, one, then another square like this, two, and a third square like this. So using this, you can cover all the columns. But since you need to cover both the rows and columns, I think it is quite intuitive that you need to place 2 into 3. 2 into 3, which is 6. Like 3 along this, then 3 along here. So total 6. Right? So I think it is quite intuitive. Like, is any doubt? Is there any doubt? Just let me know if there's any doubt. Yeah, anyways, so basically the answer is that along the rows, how many you need? N upon 2k plus 1 ceiling, and along the columns you need ceiling of m upon 2k plus 1. So this is the answer. And like in C++, how do you compute ceiling? Like if you want to compute the ceiling function of a by b, then you don't use float, because float can have precision errors. Instead, what you will do is compute the GIF of a plus b minus 1 upon b. So ceiling function of a by b is same as floor function of a plus b minus 1 upon b. And by default in C++, for positive numbers, floor division is happening. So there is no need of using floating point numbers. So like if you have two integers a and b, then doing a by b will give you the GIF, assuming that a and b are positive. So if you want to compute the ceiling, then just do a plus b minus 1 upon b. Okay. So yeah, that's the problem. Let us look at the code. Code is just one line. Um, where's the code? Okay. So this is the code. Return ceiling function of n upon 2k plus 1 into m upon 2k plus 1. And ceiling के लिए I did n plus 2k upon 2k plus 1 and m plus 2k upon 2k plus 1. All right. So this is the entire thing. Now let's move on to the next one. Okay. You are given an array nums. Pair of indices I comma j is called perfect if the condition is satisfied. I is less than j. Let a is equal to nums of I, b equal to nums of j. Then both of these should be satisfied. That minimum of bracket modulus a minus b comma modulus a plus b is less than equal to min of mod a comma mod b. Max of a minus b a plus b greater than equal to max of ab. So yeah, and return the number of distinct perfect pairs. Okay. So like this problem is just annoying. Like these expressions are quite complicated if you see. Like minimum of modulus of a minus b a plus b. So there are so many branches. Like if a less than b, then this will open as negative, and if b is less than a, then this will be positive. And similarly, if a plus b is less than 0, then it is negative, otherwise it is positive. So and also minimum will have the conversion of these two. So like it is very tough to simplify these expressions, or maybe understand these expressions by default. Like just by reading these expressions you cannot make sense of them much, right? So let us try to simplify these expressions. And because there is modulus used here, like mod a and mod b, I will do some casework. Like I'll do this casework that if a is less than 0 and b is less than 0, then what is the expression? Then if a is greater than 0, b greater than 0, then what is the expression? So like this I will make different cases and try to evaluate that what are the expressions. Okay. So basically let's try to do the casework. Okay. I'll just copy these expressions right here. Yeah. Okay, so this is the expression. So let's say we have, like, let's take the first case where a and b are both greater than 0 or greater than equal to 0. Let's say b is greater than equal to 0. Okay, so now guys, one thing that I'll ask you is that if both are greater than equal to 0, then between a minus b come odd and a plus b come odd, which one is greater? Which one is the minimum and which one is the maximum? I'll just ask you this, guys, that if a and b are both greater than equal to 0, then between a minus b and a plus b, which one is bigger? Just let me know. Just let me know which one is bigger. A minus b and a plus b mein. A plus b is bigger. Always. Okay. And why is that? Because let's just visualize it. Okay. Like I'll draw a number line. I'll draw a number line. Okay. And here I have 0. And here I have, let's say, a. And here I have b. Or let's say this is b and this is a. Okay. So what is this distance? This is basically modulus of a minus b. That's the definition of mod of a minus b, right? The distance between a and b. And this modulus of a plus b is what? You can say that this is modulus of a minus b, right? So if b is somewhere here, then minus b is here. So definitely this distance is greater. This distance is a plus b, right? Mod of a plus b. So this is greater, definitely. So if I have both positive, then a plus b is definitely greater than equal to a minus b. Okay, fine. So I can simplify the expression. Like these two expressions I can simplify. Basically, let's say is greater than 0 and b is greater than equal to 0. Right. So let's assume that a is equal to x1 and b is equal to y1. Like what I'm doing, since they are both positive, I'm assuming that a is something x1, b is something y1. Now let's say if one of them is negative, like in the next case, what I'll do, let's say in the next case, a less than equal to 0, b greater than equal to 0. When I am dealing with this case, I will assume that a is minus x1, a is equal to minus x1, and b is equal to y1. Like basically, the actual number part of it is x1. Like in the a, suppose a is minus 5. So I'll say that this 5 is x1. Okay. So I am doing that. So in the first case, simply a is equal to x1 and b is equal to y1. So let's try to simplify these expressions. So minimum of a comma b, sorry, minimum of a minus b comma a plus b, that is basically a minus b, right? As we saw. And a co I'll replace with x1 because I can do that, right? And b co with y1. So minimum of both of these is x1 minus y1 and less than equal to minimum of absolute value of a is basically x1, absolute value of b is y1, right? So this is one equality that we got, and we can simplify this even more. How? Like what is the meaning of x1 minus y1 ka absolute value? Like let's say if I say absolute value of 3 minus 5, so what you will do, you will do 5 minus 3, which is 2. So like mod x minus y1, that basically means bada wala minus chota wala, like whatever is the maximum of these two minus whatever is the minimum of these two. So this is the same as max minus min, right? So I can write this as maximum of x1 minus y1 minus minimum of x1 minus y1 should be less than equal to the minimum of x1 minus y1. x1 comma y1, I mean, not minus y1, x1 comma y1. So what I get, maximum is less than equal to 2 into minimum. Okay. So this is the actual inequality that we get from this first inequality, I mean. Okay. This is the inequality that we get from the first one. And from the second one, what we get? Let's try to simplify the second one. So we have max of a minus b a plus b, which is basically mod of a plus b, mod of a plus b, and they are saying that it should be less than equal to or greater than equal to max of mod a comma mod b. So this is definitely true, right? Like if a and b are positive, then of course a plus b, this is a plus b, right? This is just a plus b, and this is greater than equal to max of a comma b. Like because mod a is same as a and mod b is same as b, so a plus b is definitely greater than equal to max of a comma b. So this is like universal set. Like this is satisfied by every pair a comma b for positive numbers, I mean, right? So if a and b are both positive, then you get that the first inequality is max is less than equal to 2 min, and second inequality is just a truth, universal truth, right? So similarly, we can like simply deal with all four cases. Like I'll just deal with one more case for you. Like a less than equal to 0, b greater than equal to 0. So for this case, let us try to understand that what would be the simplified version. So a less than equal to 0, b greater than equal to 0, and let's simplify this expression. Can I somehow increase the font of this? Yeah. Okay. Yeah, anyways, so what I'm saying is, let's say if a less than 0 and b greater than equal to 0, then what is the simplified form? So let us replace a with minus x1 and b with y1. So like since a is negative, I am replacing it with minus x1, where x1 is positive and b is with y1, so y1 is positive. Like both of these numbers are positive. So let's replace them. So what we get? Min of mod of a minus b. A is what? Minus x, and minus b is y1, right? And a plus b, which is minus x1 plus y1, should be less than equal to the min of x1 y1. Like mod a is x1 and mod b is y1, right? So this is the first inequality. Now we can again simplify this. We can just take out the minus sign as common, and the absolute value will just eat that minus sign. Like absolute value of minus x is same as absolute value of x, right? Mod of minus 5 is same as mod of 5, right? So we can just take this minus as common, so it will become what? Min of mod of x1 plus y1 comma y1 minus x1 should be less than equal to min of x1 comma y1. Now again, we since we know that x1 and y1 are positive, so we can definitely say that this number is a smaller one out of these two. So I can just say mod of x1 y1 minus x1 is less than equal to minimum of x1 y1, and this was the same expression which we got earlier, and this just meant that min should be sorry max should be less than equal to 2 min, right? So that's how you can simplify the expression for all the possible cases, and finally you will get the same thing, that for all the four cases the answer is coming out to be max is less than equal to 2 into min. So basically, like what is it coming out? Max of x1 y1 should be less than equal to 2 into min of x1 y1. So this is what is coming out of all these four cases. So basically you just need the values of x1 y1, like x1 and y1 only you need. And what is x1 y1? Like it is essentially the absolute value. Like at this point, x1 and y1 are just the numerical values. Like if my element is minus 5, then the value of x1 for that element is 5, right? So for a perfect pair, this condition will hold, that max of x1 y1 should be less than equal to 2 into min of x1 y1. So that means we don't really care about the sign. Like at this point, we only care about the absolute value, about the value of x1 and y1. Okay. So like I'll give an example: -3, 2, -1, and 4. -3, 2, -1, and 4. So let's say I ask you that is this -3 and 4, if I take this pair, minus a is equal to -3 and b is equal to 4. So are these a perfect pair? So you can instantly say that yes. Why? Because for this the value of x1 is 3, and for this the value of y1 is 4, and since the maximum, this is 4, is less than equal to 2 into minimum, 2 into 3, so that's why it is a perfect pair. So essentially in the array we don't really need the sign, like we only need the magnitude of the number, and we basically need to find all the pairs I comma j such that um, the max of ai comma aj is less than equal to 2 into min of ai comma aj. Okay, so this is what we have to find out: the number of pairs I comma j, like after we take the mod. Okay, like after we just take the absolute value of all the elements, we want to count the number of pairs I comma j such that max of ai comma aj is less than equal to 2 into min of ai comma aj. This is what the problem boils down to. And how do you solve this? Explain again. So which part, Madhav, do you want me to explain? Okay, Red is asking, can you explain that in the last step, how did you take min of x plus y and y minus x? So, Red, did you understand here that when uh, when I asked you guys that if a and b are positive, if a and b are positive, then what is the, like, between a minus b and a plus b absolute value, which one is bigger? So I asked you this, guys. I asked you this, right? So you all said that a minus b is the smaller one and a plus b is the bigger one, and I explained that why is that so. So when a and b are positive, then this is true. So since x1 and y1 are positive, like I just defined them to be like that, x1 and y1 are positive. So um, that's why I can just write that min of x1 plus y1 and y minus x1 is definitely this term right here. Okay, didn't make sense. Yeah, after sorting, we can do it, Rishabh. Like I'll explain that. But before that, do you guys get how I um, read? Do you understand how I got it? I'll explain, Vishal. I will explain that in a minute. But first, Red, do you understand that? I'll explain I less than j thing. Didn't make sense to Suraj. So, Suraj, what did not understand about the maths? Like I just did some mathematics. So was it, like, which part was not understandable? Like you could just rewatch the explain inequality part. So the entire problem is inequalities only. So which inequality? Okay, I'll explain. Just I'll take one more case. Okay, I'll try to simplify the expression using one more case. So we have this expression right here. Okay, like as you can see, we have this right here expression, and let's simplify this for the case where a is greater than equal to 0. A is greater than equal to 0 and B is less than equal to 0, right? So let's assume that A is equal to x1 and B is equal to some minus y1. Like since B is less than equal to 0, let's assume that B is equal to minus y1. Okay. So I'll replace these values into these inequalities. So let's take the first inequality first and second we'll take later. So first inequality is this one. So I'll replace A with x1 and B with minus y1. Okay. So we get min of mod A minus B. So basically x1 is, I mean, A is x1 and minus B. So B is minus y1, right? Comma A plus B. So x1 plus minus y1, right? And RHS is basically less than equal to min of mod A comma mod B. So mod A is x1 and mod B is y1, right? Like if B is negative and I assume that B is some minus y1, like let's say B was minus 5, then here y1 is 5, right? So mod B is 5. Okay. So this inequality, that's what it becomes. Then I'll simplify it once more. So min of mod x1 plus y1 comma x1 minus y1 less than equal to min of x1 y1, right? And now you know that who is the minimum of these two. Like I told you that since these both are positive, then we can say that this one is the minimum, right? So x1 minus y1 ka mod value should be less than equal to minimum of x1 minus x1 comma y1, right? And I can write this absolute value like this. It is basically max of x1 comma y1 minus min of x1 comma y1, and that should be less than equal to min of x1 comma y1. So sorry, not less than equal to or greater than equal to. I think it is less than equal to. So I think I just messed up somewhere. Okay, no, say max of x1 comma y1 should be less than equal to 2 into min of x1 comma y1. So basically in this case, this is the result that you got. Like if you want to compare that 3 comma minus 4, is this a good pair, a perfect pair? Then you can just see that here x1 is 3 and y1 is 4, and since the maximum, that is 4, the bigger one is less than equal to 2 into smaller one. That's why you can say that it is a perfect pair. So I just solved this one case, like this case where A is greater than equal to 0, B less than equal to 0. I replace this with x1 comma minus y1. So you can just check all the cases, and you will see that in all the cases, this is the inequality that you are getting. Okay, like the first inequality is this thing, and second inequality, if you evaluate, like second inequality, okay, I'll just do that as well. So max of A minus B comma A plus B, which is, okay, I'll paste it one more time. Yeah. So max of A minus B comma A plus B, I'll replace A with x1. Mod of x1 minus B. So minus B is plus y1, comma A plus B. So x1 minus y1 is greater than equal to max of x1 comma y1, right? So here max is what? Max is basically mod of x1 plus y1 is greater than equal to max of x1 comma y1. So this inequality, like since you know that x1 y1 are both positive, then of course this is just x1 plus y1, right? And that is greater than equal to max of x1 comma y1. So this inequality is satisfied for all the numbers, right? This is obvious. Like x1, the sum of two numbers is definitely greater than equal to both of the numbers if they are both positive, right? So we don't need to worry about this inequality. this inequality is already satisfied for all the numbers, but we just need to check the first inequality, which simplifies to the bigger one has to be less than equal to 2 into smaller one, and we are only checking the absolute values. Okay. So I hope now it is clear. So yeah, now the problem boils down to we have been given an array. We have been given an array a1, a2 up to an, such that all of the ei's are positive, that is greater than equal to 0, right? And we need to find the number of pairs I comma j such that I is less than j, and also the minimum, I mean the maximum, is less than equal to 2 into minimum, right? So the problem boils down to this. This is the new problem, and I think this, you might have done this problem. Like first of all, you are asking for I less than j. So I less than j just ensures that we are counting each pair only once. Like I less than j means that, okay, let's say my a2 is 3 and a3 is 4. Then of course this 3 comma 4 is a good pairing. Like if we have a2 as 3 and a3 as 4, then this I comma j pair of 2 comma 3, it is good because the max is less than equal to 2 min for 2 comma 3, but they are asking that I is less than j. So like if they did not ask for I less than j, then we would have counted 3 comma 2 also. Like even though 3 comma 2 and 2 comma 3 have the same numbers, so of course they are perfect, they both are perfect, so we would have counted them separately. But now since I less than j is to be ensured, that's why we will only count each pair only once. So even after sorting, it doesn't really matter. Like even though we lose the information of I and j, but it just means that we need to count each pair only once. So we can simply sort, and there's no problem in that. So let's sort the array. Let's say we sorted the array a1, a2 up to an, right? Now how do I count the number of pairs I comma j? So let's say I am looking like, let's say I iterated over this array. I am iterating over this array, and let's say I look at this a2. Now what I'll do is I will count that in how many perfect pairs is this a2 the smaller number. Like let's say I have an array 1 2 4 6 8. Okay. So let's say 1 2 4 5 6 8. So let's say I am at this number. So I'll try to figure out that in how many pairs is this 2 the smaller number. Like this is index 1, right? Index 0, index 1, index 2, and so on. So if my first index is index 1, like if one of them is index 1, then how many others are there such that this 2 is a smaller one? So basically 4 is fine, right? Because 4 is less than equal to 2 into 2. Or let's say if there was a 3 here, then 3 is also fine. So basically all those numbers which are greater than equal to 2 but less than equal to twice that, so less than equal to 4, all those numbers are valid, right? So you can simply do a binary search for that number. Like you can simply do a binary search for 4. Like you can just find the upper bound of 4, which is 5, and basically you can choose all of the numbers before that. Like after this 2 and before this 5, you can choose all of those numbers, and that's the number of pairs that can be made using this 2. So you can simply sort the array and iterate over the array, and just find out that for every index how many elements can be there for that smaller element. All right, so that's the entire solution. So guys, just let me know what is the, like, is there any problem with this? Okay, so I am not getting any doubts, so I'm assuming that everything is fine. Okay, then let's move on to problem 3. Minimum cost path with edge reversals. You are given a directed weighted graph with n nodes, labeled from 0 to n minus 1, and an array edges, where edges is ui where wi, which is an edge from node ui to node vi with a weight of wi or a cost of wi. Each node ui has a switch that can be used at most once. When you arrive at ui and you have not yet used its switch, you may activate it on one of its incoming edges. Or actually, my bad, I forgot to show the code for the previous one. Yeah, so this is the code. Like, first of all, I'll just replace every number with its absolute value, right? And then I'll sort it, right? And then I'll iterate over the entire array, and for every element, I'll find the upper bound of 2 into I, like 2 into AI, right? So I can take all the elements from I plus 1 up till it minus 1. So basically, you will have it minus, like, the it position minus I minus 1. So you will have these many number of elements for the ith position. Okay, and then return the answer. Yeah, anyways, so yeah, I was reading this, that we have a graph and we have some edges, and what we can do is each node ui has a switch that can be used at most once. When you arrive at ui and you have not yet used its switch, you can activate it on one of its incoming edges, vi to ui. That means you can take any of its incoming edges and reverse that edge and then traverse it. So, like, if you are at the node ui, then you can take any of its edges, any of its incoming edges, make it outgoing and traverse it, and that will cost you 2 into wi. Okay, so return the minimum total cost to travel from node 0 to node n minus 1. Okay, so what they are saying is we have a graph. Like, let's take a test case. So we have this test case. Let me see if I can copy it. Yeah. Okay. So we have this graph right here. Okay. And we have to go from the node 0 to node 3, right? And whenever we are at some node, if we have not used the switch yet, what we can do is we can change any edge from incoming to outgoing. So, like, let's say from 0 we move to this node 1, right? So it will take us 3 cost. Then from 1, where do we go? So from 1, I will reverse this edge. Like, since I have not done it for 1, I can do it right now. So I will reverse this edge and I'll go to 3. And that will cost me 2. Okay. So in the 3 plus 2 cost, I reached this node 3. So in 5 cost, I reached this. But let's say if I didn't have the superpower, like if I was not allowed to do this, then definitely I would have to take this path 2 and 4, which would result in 6 weight. So this is the better path, 3 and 2, which is 5. So the answer for this test case is 5. And like, you can only do this thing. You can do this thing only if you have not done it yet. Like, you can only traverse the reversed edge only if you have not already done that, right? So how do you actually solve this? Now, actually, in this problem, there is only one simple observation, and if you have that observation, then there is no problem in solving the problem. Like, see, let me just tell you a solution of this graph problem, and we'll discuss that why is it correct. Okay. So, all right, in the problem, what they are saying that we can reverse one of its edges, vi to ui we can make it ui to vi, and then traverse it, and that will cost us 2 into wi. Okay. So what I'm proposing is, let's say you, for all the edges that you have, let's say this edge, this edge, this edge, and this edge, we have these 4 edges, right? So for all the edges, just build the reverse of them as well. Like, in this graph, just build this edge of 4. uh, just build this edge also of weight 6, then this edge of weight 2, and this edge of weight 8. Okay, so you have made this new graph, that is, you have added these 4 edges, and then in this graph if you find the shortest path, then that is your answer. Like, my claim is that in this graph, if you want shortest path like this 3, then this 2, like you take this edge of weight 3, then take this edge of weight 2. So taking this edge of weight 2 is the same as reversing this edge and going here, right? So that's why I made these new edges of double weight. So if you find shortest path in this graph, then this is just 3 plus 2, right? So which is 5, and that's how you can get the answer. But how does it work? So the main idea here is that going here by using this edge, and then using this edge is the same as reversing this and then using it, right? That's why we can do this. But there is one more constraint in the problem, right? There is one more constraint, that we can only do this once for every node. Like, it can be used at most once. Like this superpower, that reversing the edge, that we did here, right here, right? We reversed this edge. So we traversed this edge basically. So we can only do it at most once. But like, if we are searching for the shortest path, then what is the guarantee? Like, how do we ensure that this constraint is respected? How did we ensure that in this solution? What do you think, guys? Like, what about that constraint in my proposed solution? What about the constraint that you can only traverse it once? Like, you can only, if you are at some node, then from that node you can only reverse the edges once, or any edge you can only reverse at most one edge and then traverse it. So how is that condition respected? Like, what if in my solution I am using the reversed edge twice? Like, let's say when I apply Dijkstra, I first go here. Let's say my solution first goes here, then it goes on this path, then it goes on this path. Okay. um, then my path goes here, then my path goes here, and then again my path goes like this. So like, what if something like this happens? Like, I'm using this edge twice, right? I am using this edge twice, but that is not allowed, right? Like, here in the problem we cannot do that. So how does my solution handle that thing? So basically, what I was asking, like, how do you handle this? So my solution is like, actually, the thing is that automatically it is taken care of. Okay, the constraint that is given the problem, it is no issue. Like, see what they are saying in the problem. They are saying that each reversed edge, like, okay, they are saying that from each node you can reverse an incoming edge at most once. Like, this is the constraint, right? They are saying that for each node that you are at, you can reverse the incoming edge at most once. Like, you cannot reverse it again. So actually my solution respects that constraint also. Why? Because of this fact. The fact is, if all weights are positive, like in a graph with positive weights, positive weights, the shortest path, visits each node at most once. Each node at most once. Okay, this is the actual fact, that like if you have a graph, okay, if you have any graph, like even take this graph also. So just take this graph. So like if you have any graph, then if you make a shortest path in that graph, then definitely you won't visit the same node twice, right? Because what's the point? If you want the path to be short, then you will directly go wherever you want to go, right? Why would you come back to a node? You would never come back to a node, right? You want to just go to your destination. Because if you are coming back to a node, that means you are traveling from a cycle, and that cycle will add weight to your path. So you won't do that, right? So in the shortest path, you will definitely only traverse, like only go out of each node at most once. So if you are going out from that node using a reversed edge, then you can say that you reverse that edge. And if you are going out from that node using a normal edge like this, then there is no problem. So the constraint that you can only apply the reversal operation at most once is definitely respected in our solution, because anyways Dijkstra doesn't, like anyways we know that for each node in our shortest path, we don't go out of a node more than once. Okay, so that's the thing. Yeah. So this is the entire idea here. So the solution finally is that just in this graph, add the extra edges, like uh, alongside with this edge, make this one as well. So for all the edges, just make their reverse also, having the double weight, right? Because to traverse the reverse edge, we need double cost. So just add these edges with double weight, and then simply apply Dijkstra on the graph, right? And finally, just share the answer with the jury. What if in the question we have been given edge weight from u to v as value 1 and v to u from as value 2? Then what do you mean? Like um, in this question, like are you changing the question, or is it that there is one input in which, like what's your doubts? I don't understand that. uh, is your doubt that instead of 2 into wi we were given a custom value? Like here they are saying that from vi to ui we have wi weight, and from ui to vi, like reverse it, then it cost 2 into wi. So are you asking that instead of 2 into wi we had some other cost, like it was in the input only, that after reversing what is the cost? What if we ask that only reverse edge one time in whole graph? um then it is a different problem. Then I think it is similar to the flight routes one. Like on the CSCS, if you have done this problem called flight discount. So this problem called, or flight discount, where is this? Yeah. So this problem, if you have done it, then your question is pretty much the same. So like just try this problem first, and you can try then your problem, and I'm pretty sure you will be able to do it. Anyways, so this was the solution, and I'll just show the code now. So in the code, they have given the edges, right? So I just made the adjacency list, and so like UVW, right? UVW is the edge. So adjacency of U dot pushback V comma W, and also I add the reverse edge as well. So adjacency of V dot pushback U comma 2 into W, right? And then this entire code is just for the Dijkstra. Okay, this is standard exact same Dijkstra code, which is what that's what I would do, right? So just this Dijkstra, and finally just return the distance dot back. That means the distance of n minus one, right? Why do we need to reverse all the nodes? Just add reverse h for u to v where u is less than v. Like, why do you think, Raymond, why do you think that we cannot go from a higher numbered node to a smaller numbered node? Like, what if we want to move from 3 to 2? Like, what does it, like, u less than v का कोई sense नहीं है. Like, you are saying that only for u less than v, if there's an edge from v to u, we will reverse the edge from u to v. But that's not correct. Like, we might want to go from v to u also. Like, let's say we have the node 0 right here. Then we have node 1. Then we have node 3. Then we have node 2. Okay. And let's say it is like this. This edge is like this, node 2. And from node 2, we have node 4. And you want to go from 0 to 4, right? So starting at 0, you want to go to 4. So you will reverse this edge. You will have to reverse this edge, right? Yeah, Pradeep, that makes sense. Yes, now D. Okay. All right. So you are given m by n 2D integer array grid and an integer k. You start at a top left cell 0 comma 0 and your goal is to reach the bottom right cell m minus 1 comma n minus 1. There are these moves are available. Normal move. You can move right or down from your current cell I comma j. That is, you can move to I comma j plus 1 or I plus 1 comma j. The cost of this value, the cost is the value of destination cell. And teleportation, like you can teleport from any cell I comma j to any cell x comma y such that grid of x comma y is less than equal to grid of I comma j. The cost is 0, but you can only teleport at most k times. So return the minimum total cost to reach the cell m minus 1 comma n minus 1 from 0 comma 0. Okay. So this problem, let's discuss this. So we have like a grid. Okay. So first of all, after just reading this, you might think about DP on grid type of thing. So let's say we have this grid. Let's take the sample input 133254435. 133254435. So you are starting from here. Okay. And either you can okay, and here k is equal to 2, k is 2. So either you can move down or right, and the cost of that is the number written on the final cell. So like if you move right, then it will cost you 3 coins, right? And if you move down, it will cost you 2. Okay. So either you can do this or you can teleport. So teleport means that from wherever you are, you can teleport to any cell which is less than equal to that cell. So from 1, you can teleport to any cell which is less than equal to 1. And in the entire grid, there is no other cell like this. So we'll just ignore that thing. Let's say we move to 3. Okay. So from 3, where can we go? Like we can teleport to 2. Okay. And also teleporting has 0 cost. All right. So we can teleport to 2. And we can also teleport to 1 as well. That's allowed. Or we can teleport to this 3. So that those things we can do. Okay, or we can go either down with cost of 5, or we can go right with a cost of 3. But if we want to go here, then we just teleport, right? Or maybe not, because the number of times that we can teleport is limited. Like we can only teleport at most 2 times. Okay, so let's say we go down, so it will cost us 5, and then from this 5 we can teleport to anywhere, because all these cells are less than equal to 5, right? So we can simply teleport on this final cell, and we have reached our destination. So in this case, what is the cost that we incurred? Like we went from here then here, so 3 plus 5, which is 8. But the answer is 7, because instead of this we could have done like that. Like let's say we could have gone from 1 to 2 to 5, like normal moves, and then we could teleport. So 2 plus 5, which is 7. So the answer is 7 for this test case. Okay. So yeah, this is like your problem, that you can teleport at most k times, right? Then what is your actual distance, like, or the minimum cost that you'll incur to reach the cell, the bottommost cell, bottom right? Okay. So guys, let's say I did not have this teleportation thing. Like let's say I did not have the ability to teleport. Then how would I have solved this problem? Dijkstra. Yeah, DP. DP is better because Dijkstra is for graphs. Like yeah, we can apply DP. We can apply Dijkstra as well, but we don't need to, because it is a grid, right? It is a grid and there are no cycles in it. There are no cycles in it, so we can apply DP only. So like we will store the DP, that let's say I store that DPIJ DPIJ is equal to the minimum cost to move to go to the m minus 1 comma n minus 1, starting at I comma j. So basically, dpij will be that what is the minimum cost to go to this cell if I start at I comma j. So I can recursively try to find the answer. Like basically, what is dp of I comma j? Dp of I comma j will be equal to the minimum. Like either you can go down from I comma j or you can go right. So the minimum of dp of I plus 1 comma j plus the grid of I plus 1 comma j. So you go right in, or you go down in this case, or you can go right. So dp of I comma j plus 1 plus grid of I comma j plus 1. Right. So this is the transition for this dp. So like if we did not have the ability to teleport, like if we were not allowed to teleport, then this is what our dp looks like. And where did that go? Okay. So that's what our dp looks like. So until here, is it fine, guys? It's just standard problem, right? Normal dp approach, correct? But here now we have an ability that we can teleport as well, right? So what do I do? And like we can only teleport until k times. Like it is limited. So we have been given a k, and we can only teleport in the grid up to k times, right? So okay, let's look at the constraints for now, just once. So here I and j are given to be up to 80. I mean the n and m are up to 80, and k is until 10, right? So these constraints are pretty small, right? So what we can do is we can try to, like, basically we can add one more state to this DP. Like what I'll define my DP as, DP of ijk. DP of ijk will be that the minimum answer, minimum cost, or not k. Let's take k is already defined, right? DP of ij moves. DP of ij moves basically means that the minimum cost to reach um, n minus 1 comma n minus 1, if if I have already performed moves teleportations. Like this moves is a number, okay, this is a number, right? So if I have already performed these many teleportations, then what is the minimum cost that I have to incur? Minimum extra cost, I mean, like starting from this state, if you want to reach to n minus 1 and minus 1, then what is the minimum cost? Okay, so this is my DP state. So how do I transition? Like if I propose this state, then how do you transition? Let's think of something. So let's say I have this grid, right? Like I'll just take a sample. I have this sample, right? So I will okay, wait, I'll copy this and I will paste it here. Yeah, so here in this grid, let's say I want to find out, here k is 2, okay. So let's say I want to find out that what is the value of 111. Like this is row 0, row 1, row 2, column 0, column 1, column 2. Okay. So let's say I want to find out that what is the answer of 1 comma 1 comma 1. Okay. So what does this mean? Like starting from this 1 comma 1 cell, and if I've already performed one teleportation, then what is the minimum total cost? Right. So from this state, where can you go? So like when you are here, what all can you do? So either you can move right, or you can move down, or you can teleport, right? And even teleporting, may you have many options, right? Okay. So let's say you move right. If you move right, then to which state will you go? You will go here, right? So basically you go to DP of 1 comma 2 is the cell position, and the number of teleportations is still 1. Like because until now, starting from 0 0, when you reach till here, you have performed one teleportation until now, and now you go right. So that means until here also you perform one teleportation. Like the number of teleportations don't increase by performing, like going to the right, correct? So this is the DP of 1 comma 2 comma 1. Or if you do like this, like if you go down, then this is DP of 2 comma 1 comma 1. Like you go here and you have only performed one teleportation. Or let's say you teleport. So where can you teleport to? Where can you teleport to? So you can teleport to actually anywhere, right? Because you are at 5, and you can teleport to all the cells which are less than equal to 5. So all these cells are less than equal to 5. So let's say you want to teleport to this cell right here, which is 1 comma 0, right? So you can say that you can go to DP of 1 comma 0 comma 2. Why 2? Because until here you had performed one teleportation, and now you perform one more. So now you have performed two teleportations, right? And you actually, from this you can no longer teleport, because you already, the limit of k was 2, right? And so you cannot do more than 2. So from this state you cannot teleport, and that's the reason that we were keeping track of how many times we have teleported, right? So okay, how do we find the answer actually? Like, if we want to find the answer for this 1 comma 1 comma 1, then either we can go right. So what is the cost for that? The cost is like basically the final destination, right? So grid of 1 comma 2, grid of 1 comma 2. So the cost in doing this move is grid of 1 comma 2, and then going from there to our final destination is dp of 1 comma 2 comma 1. So the actual answer would be dp of 1 comma 2 1 plus grid of 1 comma 2. Then if you go down, then it is dp of 2 1 1 plus grid of 2 1, right? Or if you teleport, then it is zero cost, right? So the answer is just this. So you can simply explore all the options and figure out that what is the best one. So what is the minimum one, and that will be your answer to this dp, right? So this is what your actual solution is, but there is one problem in this. That what is the rank complexity of this? Like, see, you have this state, right? You have this state, and you are checking that from this state either you can go right or you can go down, or you can teleport. So total in the worst case, how many transitions are there? How many transitions are there? So there are in total m into l cells, m into n cells, right? And like if this cell is the highest, like if you are here and it is the highest, right? So you can go to any of these cells, you can go to any cell, right? So there are mn transitions for teleportation and plus 2 transitions for down and right. So in total you need to check total mn plus 2 transitions for this state. And the number of states are what? The number of states are m into n into k, right? Our dp was this dp of I comma j comma moves. So n into m into k plus 1, because the moves can be from 0 to k, right? So k plus 1 into m into n. So basically O of k into mn raised to power 4. So I think this would give TLE, because mn can, like mn n are up to 80, right? So let's calculate this. So 80 raised to the power 4. So 80 into 80 into 80 into 80 into 10. This k is 10, right? So as you can see, this is four zeros, these four zeros. So it is 4e8, 4e8 operations. So it might be possible that you might get away with this, but it is borderline, and definitely is not intended by the lead code setters, right? 4e8 is never given in a problem. Okay, like the internet solution will never work this slow. Okay, so all we need to do is think of a better way to transition. But this is a working way. Like if you ignore TLE, then this way is a working. Okay, and where did it all go? Yeah. So if you don't worry about TLE, then this DP just works, and in fact it works in 48 times. So like in 5 6 seconds it will run. But how do you optimize this? So first of all, do you guys get this approach? How I solve this? Yeah, it is giving TLE, right? Yeah. So how to efficiently store the possible teleport teleport coordinates, right? Yeah, it is also DP. In fact, the state is also same. In the optimal solution, the state is also the same. Just that the transitions are a little optimized. Okay. So how do you think you can transition? Any ideas, guys? Sorting based on values. So after sorting, what you will do? Like Okay, you sorted. Then what's the idea? We can store in the map from each cell where we can go. But yeah, that's fine. But what if from each cell you can go to every cell? Like let's say every cell is of the same number. Then from each cell you can go to every other cell. So that will still consume n into m power, like n into m whole square into k. So that thing is still a problem. Like transitions will go from 0 to lower bound of current value. Yeah, that's true. But the thing is that that's the issue. Like what if there are so many? Like how will you'll still have to iterate over all of those, right? You will still have to iterate from 0 to lower bound. And what if the lower bound is the last? BFS, I mean DP is BFS only. I mean, not like here the problem is that your dependency graph is too dense, right? You have to kind of optimize the transitions. I think we will do teleportation of a number only once. K will exclude in that case. Um, how is that? Like your state will have the K, right? Like my state is I comma j comma number of transitions. I mean, my state was that the starting cell I comma j comma how many times have I already visited. So that's where the K was coming from, the number of states. So if you are saying that K will not come, then that means you have changed the state. So how what state did you make? Like in that case, it is a completely different solution which I don't know about. Yeah. Anyway, so I'll just try to give you guys the intuition of this. Okay. So the main idea here is to observe the board like like just try to visualize the board. Okay, the grid. I mean, so here you have this grid, right? Again, I will paste it somewhere. Let's say I paste it here. So we have this grid. Now the point is that okay, let's say that this grid corresponds to moves equal to 0. Okay, so like um, I am here and moves equal to 0. That means this cell corresponds to the state 0 comma 0 comma 0. Okay, this cell corresponds to the state 1 comma 1 comma 0. Okay, so just visualize this, that either you can move right or you can move down, and in that case still moves will be equal to 0, or you can teleport. Actually you cannot teleport from this state, so I'll take another one. I'll take this one. So either you can go right or you can go down, right? So in this board only that will happen. But if you teleport, then you will have one more copy of this board. Like you can think of it like this board is for moves equal to 1, and you are transitioning. Let's say if you teleport from 3 to 2, okay, then you are going from here to here, from this to this. Okay, so from this 3, where like where can you go? You can go to this 2, you can go to this 3 also, or you can go to this 3, or you can go to this 3, or you can go to 1, right? These are all the possible transitions that you can do from this 3. I mean like what, these teleporting transition, like either you can go down or right, or you can teleport, right? So you have these 5 options to teleport like this. And let's say that you know the dp values of all of these. Like in dp, what do we do? In dp we simply try to find the answer recursively, right? That to find the answer of this state, that is 0 1 0, I will have to first find the answers of these all states. these states and also these two states. So let's say you have the answer for all these states in this moves equal to 1 var thing. So like in this layer, if you have all the answers, then from this 3, if you want to teleport, then where would you teleport? Can I just say that you will teleport to the minimum one? Can't I say that? Can't I say that you can just teleport to the minimum one? Right? Out of these 5, you will teleport to the cell having the minimum answer. Right? Because the cost to teleport is 0. Right? So you will just teleport to the minimum one. But how do we find the minimum one? Except for iterating over all. Like there is one way that we iterate over all the possible teleportations. But if we want to just find the minimum, then what can we do? So the main idea here is you can store all the answers of this grid in form of sorted array. Like here all the numbers are there, right? Like this 1 is there, 2 is there, 3 is there, 4, 5, right? So let's say you just found out the answer of these. Like somehow you have the answer of this layer and you want to find out the answer for this layer. So what you will do is you will store the answers of this layer in sorted order according to these numbers. Okay. So like what you will do is first, like I'll store an array. You will store an array of size 9. Okay. You will store an array of length 9. Okay. And in the first element, like basically what the idea is, just sort all of these cells by their value. Like this 1, 2, then 3s, then 4s, then 5s. So just sort all of these cells by their value, and then in the increasing order store the dp value. And why is that helpful, I'll tell you. So okay, first let's say I have this cell which is 0 comma 0. Like okay, the index 0, index 1, index 2, index 3, 4, 5, 6, 7, 8, right? This is extra, just ignore this. So let's say the smallest cell I have is 1, right, which is 0 comma 0, and let's say the answer to that is 5. Just hypothetically the answer is 5. Then next cell, the I have 2, so which is 1 comma 0, and the answer to that is 3, let's say. So basically you will just store this dp array. Like you will store the answers in this format. Okay. And then let's say you want to find that what is the minimum answer if you teleport. Like let's say if you teleport from this 3, then what is the minimum answer? Then the entire point is you can teleport from this 3 to any cell which is less than equal to 3. And since we have stored the answers in this sorted format, then your answer is just the prefix minimum. Okay, like see, here the answer for 1, the answer for 2, then we have 3 3s, right? So in these 3 cells, we will store the answer for those 3 cells, right? So if we want that to teleport from this 3, where do you go? Like if you go somewhere, then what is the minimum answer? And like you can only go to less than equal to 3. So in this array, these cells right here, like these cells contain the answer for all these cells less than equal to 3 in the next layer. So you can just simply say that you will take the minimum of this. So for any cell, if you want to find out, it is just a prefix minimum of this array. Okay. So like when you calculated this answers, like for this layer 1, when you calculate the answers, you will just make this prefix minimum array also, right? And you will also make that what is the sorted array. Like you will just sort the values and then find out that where is the last 3, and until that index you can take the prefix minimum. And that's how in O of 1 you can transition, right? So you are transitioning in O of 1, and there are total n into m in n into m into k states. So basically total complexity would just be O of n into m into k. But just that you have to store these extra things that what is the answer, like store this array in sorted order. I mean, the array is not sorted, but in terms of the values written on the grid. Okay, so this is the idea. um why the size of 9? See, let's take a 2 by 2 grid. Okay, let's say I have 1 3 4 6. So let's say you have the answers for this. Like I had the dp state, right? The dp state was ijk, I comma j comma moves, right? So as I told you that from this moves equal to 0, like let's say if you are at 0 1 0 and you want to go to, like either you can do what you can do, you can go down to 1 1 0, or you can go right to 0 2 0, or you can teleport. So while teleporting you will go to something something 1, right? So I am drawing all the zeros, like moves equal to 0 states here and moves equal to 1 states here. So you can go from this 0 to 1 by teleporting. But where will you go exactly? You will go to the one which has the minimum answer, right? Just 1 minute. Yeah, so I was saying that if you want to transition from this 0 1 0, then of course you will go to the minimum. Like either you will go down or go right or teleport, whichever gives the minimum. So if you want to find out efficiently that after teleporting, sorry, after teleporting, what is the minimum possible answer? Then from this three, where can you go? From this three, you can go to all the cells which are less than equal to three, right? So the main idea here is that store the answers of every cell and keep it in such an order, like in increasing order of the values. Like okay, let's say I have 1 3 4 and 6. Man, this is pretty annoying. Okay, we have 1 3 4 and 6, and here also I have 1 3 4 and 6. Like this is my layer 0, that means moves equal to 0 state, and this is my layer 1. So from this 3, where can I go? Either I can go down, I can't go right because there is no cell there, so either I can go down or I can transition, I mean I can teleport. So either I can teleport to this 3 or to this 4 or to this 6, right? And let's say I have the answers for this layer, like I have already calculated the answers for this layer 1. Okay, so let's say the answer is what? I'll mark the answer by red. So let's say the answer for this one is 5, this is 7, this is 3, and this is 4. Okay. So let's say you want to teleport from this 3, and you can teleport to either 3, sorry, not 3 4 6, my bad. You can teleport to either 1 or 3, right? The less than equal to that. So you can either teleport to 1 or you can teleport to 3. Okay. So of course you will teleport to 1 because it gives the smaller answer. So 5 is smaller answer, so you will teleport to 5. But how do you find it out without actually iterating over all of these? So the main idea here is that just store these answers in increasing order. So like you have 4 cells, right? You have 4 cells, and so the smallest cell is 1. So I'll store the answer of that at the first position. Then second smallest is this one, so I'll store the answer of that in second position. Then the third smallest is 4, and the fourth smallest is 6. So this is what I have stored. Like when I am computing this answer for the first layer, I have made this array. I have made this array, and also I have made one more array of the values. Like I have just taken all the values and I have sorted them. Okay, so 1 3 4 and 6. So they are the values, right? 1, 3, 4, and 6. So I just took the values from the grid and I sorted them. And correspondingly, I stored the answers also. Like for 1, the answer is 5. For 3, the answer is 7. For 4, the answer is 4. Not 4, I mean, wait. For 4, the answer is 3, right? Just a second. Yeah, my bad. For 4, the answer is 3. And for 6, the answer is 4. Right? For 4, the answer is 3. For 6, the answer is 4. So I have made these two arrays. Okay. And using these two arrays, I can simply use the prefix minimum. Like I will make one more array, which is the prefix minimum. So what's the prefix minimum for this array? It is 5, 5, 3, and 3. Right? So what I can do is, let's say I want to see that from this 3, if I want to teleport, then what is the answer? So from 3, I can go to either 1 or 3. That means I can choose anyone from the two indexes, from the first two indexes. So from the first two indexes, what is the minimum? So that means what is the prefix minimum on second index? So you can simply look at this value. You can simply make a prefix minimum array and find out the prefix minimum of this prefix. Okay. So this is your answer. Like if you want to teleport from 3, then the minimum answer you can get is 5. Okay. So that's the thing. Will we add separate independent DP for pre-computation of the array? It's 3 and 6. What is 3 and 6? 1, 3, 4, 6. 1, 3, 4, 6. And the answers are 5, 7, 3, 4, 5, 7, 3, 4. So what do you mean by, what do you mean to say? Will we write a separate independent DP for pre-computation of the array? See, first you will calculate, like you will have a DP table, like the normal DP table, which stores the answer for ijk, right? 3D DP table. So you will have this 3D vector DP of ijk, right? But like what you will do is you will evaluate this DP in the reverse order. Like because to calculate the answer for layer 0, you need the answer for layer 1, right? And to find the answer for layer 1, you need the answers for layer 2. So what you will do is you will find out the answers in the reverse order of k. Like you will find the answers in reverse layer order. So first you will find the answer for the last layer, that is the kth layer. Okay, then using that you can find the answer to the k minus 1th layer. And see, in the kth layer you cannot teleport, right? You cannot teleport from the kth layer. So the answer is easy to find for the kth layer. And then what you will do is, so you found out this DP table, and then you will also sort these values according to the value that is there in the grid. So you have these, like for the kth layer you have n into m values of the answers, right? And you will sort them according to the value written on the cell. All right. And when you want to find out the answer for this, you can simply query for the lower bound or the upper bound -1 and just the prefix minimum. And yeah, so after computing that array of n into m length, also compute the prefix minimum array, right? So that will just take off n into m time for each layer. So that is no problem. But you while transitioning, you can simply use that prefix minimum array and find your answer. Mathematics lover, like if it is difficult for you to understand that, then I think you should practice DP a bit more, like basic DP problems. This is some advanced DP. Like the states are simple, but the transitions to optimize it is somewhat tough. So before that, you should practice the standard DP problems before attempting this. Any other doubts? I'll show the code. Actually, the code is pretty complicated. I have written it in a bad way. Hmm. Okay, I'll just show it. I'll show it in VS Code. Yeah. So the code is here. Um, min cost is the function. So I am defining an NNM, right? And I have this DP. Like this dist array is just the DP. That what is the answer for IJK, right? So I have this 3D vector. Then I have the values. Like basically this array. Okay. This array which is 1, 3, 4, 6. Like if I have been given this grid, I'm converting it into the sorted array. Okay, and I'm also storing with along with it the coordinates of the numbers. Like I have a vector of pair. Like in the first thing I am storing the number, and in the second item I have the coordinates like I comma j value. Okay, so I am just pushing back grid I comma j comma I comma j. So I'm just storing this vals array, and then I'm sorting it. So that's how I have made this array right here, right? Then I have pos array. So pos is just a 2D array which gives me that, okay, let's say, see, what is this array? This array is 1, 3, 4, 6. And actually in my code, I have also stored the coordinates as well, right? So along with 1, I am storing 0, comma 0 in a pair. And along with 3, I am storing 0, comma 1. And with 4, I am storing 1, comma 0. And this is 1, comma 1. So actually this is our array. This is the array that we have. The first element is this, second element, third element, and fourth element. So the position of 0, comma 0 in this array is 0. Like index 0, index 1, index 2, index 3, right? So position of 0, comma 0 is 0. Position of 0, comma 1 is 1. 1, comma 0 is 2. 1, comma 1 is 3. So I am storing the position of every cell also in this array. Okay. So the position, like I'll just iterate over this array, and the position of this is I. Okay. Then I have these two arrays, which is the answer. Like I have these two arrays for every layer, right? So I have a vector of vector. So each vector, like sorted list of k, is the uh, is the array, like is basically this array right here, the sorted distance. I mean, yeah, distance is just the answer. Okay, so each array in this vector of vector corresponds to one layer, right? And then its prefix minimum also I'm storing. Okay, then we have, like I'll iterate over the layers. Like I will evaluate the answer for all the layers starting from k down to 0, right? So now first of all I'll try to teleport. So like if I teleport, like let's say from I comma j, like I'll iterate over ij. So from I comma j, if I want to teleport, then what is the answer? So for that I will find out that till what index can I go. Like if I want to teleport from 3 right here, then I can go to either 1 or 3. So in this sorted array, I can go to index 1, like either 0 or 1, because I cannot go to 4, it is bigger, right? So I am just binary searching for that. So upper bound of grid ij, right, essentially. And then I will just try to teleport. Like the dp for ij nums equals to dp of I minimum of dp of ij nums comma prefix minimum until that index minus 1 above on minus 1, right? In the layer of nums plus 1. Like if we are currently finding out the answer for this 0th layer, then we'll get the answer from the first layer, the prefix minimum answer, right? So this is the jumping part. Then um, then I'll just do simple dp. Like for the current layer, I am finding out that if I only go right and down, then what is the answer? So the base case is that the bottom right answer is 0, and I'll just iterate over I equal to n minus 1, I greater than equal to 0, I minus minus, j equal to n minus 1, j greater than equal to 0, j minus minus. And we have, like, okay, either we can go down, or actually this is push dp. Okay, like from where can I come to I comma j? That's what I'm doing right here. So either I can go from the above, either I can come to I comma j from the above cell, or I can come from the left cell. So these two transitions I'm doing, and after that we have the answer for all of these. Like after this for loop, I have the answer for the layer, for the current layer, right? And then I just need to fill those answers in sorted way, in the sorted way, right? So for I equal to 0 to n, j equal to 0 to m, I will just fill the sorted array, like sorted list of current layer comma position of I comma j. That is for this cell, I am storing my answer in the correct position wherever it belongs, right? And then I just take the prefix minimum of this array. Sorted list of nums, it is an array, and I am storing its prefix minimum in the prefix min of nums, right? And finally the answer is just distance of 0 0 0. Okay, so this was a pretty like implementation heavy question. The idea was not very tough if you are experienced in competitive programming, but implementation wise it was kind of annoying, let's just say that. But if you did not get this, then I think you should learn, like, practice more db problems, standard db problems first, and then try this one. No way it is 2000. I think at max it is 17 1800. All right, 1.5k. Like I don't know what is on Leetcode. Like on Leetcode I don't know what is the average thing. So I can't comment. Yeah, no, Siddhant, I don't think it is possible because we'll need the prefix minimum. Yeah, because Pradeep, this problem is pretty, like, kind of standard only. The on CF, like, tougher ones have come before. Recursive is not possible, Arshit. Like in this problem, I don't think it is possible to do it recursively because you need to compute the prefix minimum also. So that is not really possible. Have you seen similar questions before? Yeah, I guess, like, many are there on code forces. If you search for DP, then you will find even tougher problems than this. Like 1800 DP, 70 to 1800 DP is like this only. Like all these problems are. Yeah, wait, I found one. So this problem, Igor and Mountain. So this problem, I think this one is also pretty similar. Like it uses prefix sums concept, not prefix minimum, but prefix sums. But it is pretty similar. Upper bound actually, this vals array, which I'm doing upper bound on, this vals array contains a pair, right? This vals array is a pair where the first element is the value and second element is my coordinates of that, right? So to find the upper bound, I have to give it the same type, like pair of like pair of pair, right? So I just give um in the first parameter the grid of the first parameter the value that I want to find the upper bound of, because it will compare using that. And if that is the same, like while it's comparing two pairs, it will first compare the first element, right? So it will compare using this element. But if it is same, then it will go to the second element. Okay. And if you want to find the upper bound, then just give it a big value, then it will find the upper bound for you. And if you give it like -1 it will find the lower bound. Yeah, that's Siddhant Vani. I mean, prefix computations, there are many, like, yeah, there are many problems on that, but not necessarily only that. Like, on even higher scale or even higher rating, there are many other optimizations like convex hull trick or NUT optimization, like many other things are there. But on lead code, maybe I guess you will not see those things. Maybe you can optimize in segment tree, the DP. But anyways, Drunken Master, I don't have any idea about the OS and what they ask in those. I'm sorry. How long did you take in master? How long did you take to master DP? I wouldn't say I have mastered DP until now. I'm still learning. So that is a pretty subjective question that you are asking. There is no correct answer to it. Suraj, should I do CP in fourth year? Like I, I'll be frank with all of you. I have been doing CP since my first year because I was interested in it, and I did not know about its effect on the interviews and OAs and all. I just did because it was fun to me, and I don't know whether it is beneficial to do CP or not, because I don't know it. I don't do it for the benefit. So I really have no idea about the recruitments and all. So I'm not the best person to ask about that because I'm in third year only right now. So I really don't have any idea. And like I just got like internship using the campus interns, right? So I don't know what's going out in the actual world, the real world. So please don't ask me for the advice about internships and jobs. Uh, like the college, like there is a club in our college called PAG, and like currently I'm the head of that club. But when I was in my first year, actually every year they conduct lectures about CP, and so I attended those lectures, that how to get started with CP and all. And like the seniors here, they motivate the freshers to explore everything. So like I tried CP and I liked it, so I continued it. Can you tell me what CSCS problem set? CSCS is basically a set of, I think, 400 problems now, 400 problems, and it's basically very standard problems. Like mostly whatever you see here, they are very standard problems. And if you do all of these, then your theory wise, your skills will be quite good theory wise. Like graph algorithms are, like, I think all of them are here. Okay. But practice wise, they are not very, like, practice you have to do more than this also. So not just CSCS is sufficient for to practice, but to learn the algorithm, it is good. Harshit, It is just practice only. Like just practice problems having rating 1800, 1900. Okay, CSES is just CSES.5. Intern seek, I have no idea इतना सही है या नहीं. Like, anyways, let us. Yeah, Akshay, you can try CSES. डीपी के सवाल काफ़ी अच्छे हैं उसके. बट मोर देन दैट, आई थिंक कोड फोर्सेस पे इफ यू ट्राई द problems of DP having the rating of 17 to 1800, then they are pretty good. Okay, so just try them. Anyways, let's end this now. I'll see you guys later. Bye bye. Yeah, it will be shared in the description.